Yes, thank you for the invitation and the kind introduction. Hello to everybody, also hello to the people online. And if you have questions in between, don't hesitate to interrupt me. So, weighted topic is weighted full dimensional change point detection in functional time series. And so I will first talk a bit about functional data. And how functional data is different from multivariate data. When I will talk about how to detect upward changes. This is a little recap of things I've done in the last 10 years. And then the last two are the new stuff, which I did together with Claudia Kirch, also from Magdeburg, and Hedvika Ranosova from Charles University in Prague. So when we will talk about this weighted functional statistic with this, and then we also talk not about abrupt changes, but gradual changes in the end. Okay, so what's multivariate data? That's easy, right? Just you observe vectors, finite dimensional. So you can always represent them as element of R to the power D. So in R to the power D, all norms are equivalent. So you don't have to worry too much about which norm you use on this vector space. So what you do is Euclidean norm, because this is related to the scalar product. Okay. Now what's functional data? Functional data is a function as an observation. Every observation is a function. You can add functions. You can multiply functions with the scalar. So in this sense, functions are also vectors living in a vector space. But now we have infinite dimensional vector spaces and where the norms are no longer equivalent. So there are many different norms. You can have the L1 norm on the space of absolutely integrable functions. You can have a L2 norm, the space of in the space of square integral functions, or the supremum norm in the space of continuous functions. And now we have a continuous function on the interval 0, 1, so it's also bounded, so it's integral, square integral. You're free to choose one space. And now, in recent years, Dieter and Kokot and Bastian have considered the C01 and L1 space. And now I can say somehow the L2 space is in the middle. So this way, this new research gives me a new argument for my old research. Well, I can say this L2 space is a compromise. This talk will be about compromises a lot between the space of bounded function, integral function, between lies the space of square integral function. But the reason we started studying in this L2 space in the beginning was not because this is a compromise, well, because this works for a lot later, but because of mathematically simplicity, because this space of square integral function is a Hilbert space. So let's concentrate on this L2 space, which is built by H, because it's a Hilbert space. It's a Hilbert space with inner product. So inner product of f and g is the integral from 0 to 1 f of t g of t dt, and the norm is the square root. So, and when it's a Hilbert space, you have a Hilbert space basis, and you can identify this with r to the power n like natural numbers. So here I have r to some power, here I have r to some power. What's the difference here? This power is d, it's finite, and it's much smaller than n. We are not talking about high-dimensional data in this talk, really multivariate, but small dimensional data if you want to. And here we have infinite dimension. Now you can ask the question, so what? You can calculate things in infinite dimensional spaces, for example. A sample mean you can calculate even if your vectors are infinite dimensional. Okay, so let's talk about very basic things first. You know, from like your first statistics class, that's the t-test. We want to test the hypothesis that the expectation is zero, where you have real valued random variables, which are IID. How do you do it? You calculate the sample variance, then you calculate the sample mean, and you standardize by the sample standard deviation. And if this quotient is large, you reject your null hypothesis that the expectation is zero. Or if you want to, you can also square the t-statistic if you think this is more beautiful. Doesn't matter because squaring on the positive free line is a monotone transformation. Doesn't change your test. Well, so easy. One step further, you have a multivariate setting. So we have now IID vectors. We want to test the null hypothesis that the expectation is zero. Now it's the zero vector. What do? You estimate the covariance matrix. And when you divide by the covariance matrix, meaning you take the inverse of the covariance matrix. And you multiply from left to right with the sample mean of these vectors. And you get test statistic, which I call t-square, because it's similar to the t-square which we had before. And also because it's called Hotelling's t-square test statistic. You see, so multivariate data is not so much different from this univariate data. The test statistic is basically the same, only involves some matrix multiplication. Okay, so now I go more back. I now go to maybe the first or second semester, some linear algebra. How do you calculate the inverse of a matrix? Well, one possibility is you make the diagonal transformation of this matrix and then take the inverses of the diagonal elements. So the estimated covariance matrix is symmetric and hopefully positive definite. Then you can diagonalize it with positive eigenvalues. You get such a representation. B is a basis change matrix, and the inverse is given by this. Okay. So now functional data. As I turned out, the dimension is infinity. So infinity is always larger as your sample size, no matter how much data you have. So, but this estimated covariance matrix, here we've got to get the tensor product, but no matter. That's n vectors multiplied with another vector. So it's a sum of n rank 1 matrices, or rank 1 operators. So the maximum rank you can get of this estimated covariance matrix is n, and n is smaller than infinity. So you don't get a matrix of full rank. So you cannot calculate this t-square statistic. And that's the key problem why functional data is different from multivariate data. Okay, what can you do? One solution, very popular, is some form of dimensional reduction. So you project your data on a finite dimensional subspace. And when you have a multivariate problem again, and you can do Hotelling's t-square test. So you can do this with any finite dimensional subspace of your choice and any basis of your choice, of course. But when it's not clear if this basis will capture the main features of your data. So people like to use some data adaptive basis, like principal components. PCA for principal components analysis, and It's now a functional principal components, but doesn't matter. So you make an eigenvalue decomposition of your variance covariance matrix. So in functional data, it's an infinity by infinity matrix, but doesn't matter too much. Then you sort for eigenvalues by size. So lambda 1 hat is the largest eigenvalue and the second largest. At some point, you will only get zeros, right? Because this is not a finite rank, so you have finitely many positive eigenvalues, and then you have only zero as eigenvalues. So when we choose a D1 by dimension we want to have, and we project on the eigenspace associated with the D1 largest eigenvalues. And then we can use the Telling's test for the projected eigenvalues. So that's one solution. And I brought you this matrix. So we have this infinite dimensional matrix, which only has zeros after some point. Here we have the positive eigenvalues. It's lambda 1, lambda hat n, possible is a less. Whenever you choose a D1 and you take the inverse of the first lambda hat 1 to lambda hat D1, and the rest you take to 0. Meaning with eigenvalues which are 0, you keep at 0. And also the very small eigenvalues, you don't invert, but you set to 0. And then you use this to calculate its kind of, so you do pseudo-inverse. So that's the idea of function principal components. So finally, you cannot divide by 0, so it's a good idea to set it to 0. And also the last eigenvalues, which might be very small, so the estimation error for them might be quite large. Well, so maybe not so trustworthy. Maybe also a good idea to set it to 0. So we have this blue is the original eigenvalues. Then you multiply the first one with the inverse, so you standardize them to 1. And then the later ones you just set to 0. What's what you do in functional principal components. And then you might notice maybe here I have chosen D1 with three eigenvalues. So the third and the fourth eigenvalue are not so much different, but I treat them very differently. One I standardize to 1, and the next one I just set to 0. So that's one problem with functional principal components analysis. Yes?
Maybe I didn't really understand what you mean by size of eigenvalues. Like how much proportion they make to the overall sum of eigenvalues?
Well, you could do it. Doesn't really matter. So there's some values. It could be the values just of the eigenvalue, or it could be, I don't know if I add up to 1. I don't think so. No, it's long time I generated, but it doesn't matter. So the eigenvalues are some sequence which just falls down. As you see.
And it eventually terminates.
Yes, well, but I have only drawn like few, like 7, not infinitely long.
And what is the threshold? So when are you cutting off? What is you have a size where you're like, okay, now this is.
Normally, people use it a way that you explain 80%, that's very typical of invariance, or 90% of invariance.
Okay.
Right, so but no matter what your cutoff is, it might happen that very similar eigenvalues are treated quite differently. So this is what I here said. Probably somehow arbitrary cutoff, you can have different rules, and then little different estimation of eigenvalues might lead to different dimension you're treating. So this is why I'm not the greatest fan of this principal component analysis. So, and here, and then people told me, you have to do dimensional reduction. 2 professors independently told me, you have to do dimensional reduction. There's no way around it. And well, sometimes there is a way around it. So there's a problem. We cannot really estimate this variance covariance matrix well in a sense that you can invert it. But well, if you can estimate it, then just leave it out of your statistic. So before we had this statistic, there's this inverse of a variance covariance matrix in the middle. Now we have a test statistic, just leaving this variance co-matrix matrix. You don't put it there. You just take the product. This is the inner product, like the scalar product of the mean with itself. So you estimate how large your squared norm of your sample mean is. This is a reasonable test statistic to test whether your expectation is zero or not. And you don't have to do all this estimation stuff. And this is equivalent to keeping all eigenvalues, but not standardizing it. So, so this approach does work, comes with its own set of problems. So the asymptotic distribution now depends on the covariance operator. For the Hotelling's t-square statistic, it was asymptotically chi-square distributed. So you know the distribution. We can have tables. Here, you have to find out what's the asymptotic distribution, and then you, for every data set, basically, you have to evaluate the statistic with some numerical methods, something like this. But these problems can be solved. We need some probability theory in Hilbert spaces and some bootstrap. Okay. So this was background on functional data. Now I promised you change point detection. So let's start with simple change point problem. At most one change and abrupt change. So we have a series of observations. We model, of course, as a sequence of random variables, and we have a null hypothesis that all have the same distribution. And we have the alternative hypothesis that we have at most one change of the distribution, meaning the first k random variables have the same distribution when the distribution changes, and when the following n minus k random variables have a different distribution. And maybe the distribution difference because we have a different expectation. So we might have a picture like this. This is the expectation from the first k observations. This is the expectation from the following observations. And because we have random variables, we're fluctuating around. And now the thing is, it's interesting, there exists a k, meaning we don't pre-specify the k. We don't say the change will either not happen or will happen on day 27. Then it would be a two-sample problem. We would split our sample at the day 27 into two samples. But it could be at day 27, but could be also at day 15 or 31 or whatever. Okay. And now we want to do this in the functional space. And then the older approach is by Berkish and co-authors from 2009. It works with dimension reduction. So we do the same as for testing for the mean. We use functional principal components. And we choose the largest eigenvalues. We project on the eigenspace belonging to the largest eigenvalues. So under independence, say we also have when the projections on the different dimensions are uncorrelated. So let's look at this test statistic, DR for dimension reduced. We will have this later. How does this work? So we work our way from the inside to the outside. So from inside, we have a test statistic in one dimension if we would know the change point. What would we do? We would compare the first k observations, so we sum up to k, with the overall mean. Under the null hypothesis, we would have that the overall mean is a good estimator for the expectation, is also a good estimator for the expectation of the first k random variables, because all have the same expectation. So you expect this, well, will fluctuate around 0, but not very, no systematic deviation from 0. Under the alternative, and if a change would be at k, then we have that the mean of the first observations, the expectation is different from the last. So it's also like different from the pooled expectation. So we have some systematic deviation. So I hope that I've convinced you that this inner thing is a good test statistic for one change point if you know the time of a change in a one dimension. The next thing is we combine the different dimensions. And here we divide by our eigenvalues. This is how people do it is in functional principal component analysis. And then sum it up. And then, because we don't know the time point, we take the maximum over all possible time points. Okay. Now, I said I'm not the greatest friend of functional principal components analysis. So can we do something without it? Yes, we can. Well, let's first look at this later one. So fully functional FF statistic. You see the same statistic as before. Now we don't divide by the eigenvalue. That means that the variances of these things decreases. And that means that we can sum up all the way to infinity. And the sum will converge. Before we couldn't do this, because these things all have the same variance. So if you would sum up to infinity, the variance would explode. Okay, so, and then we take the maximum of all times. So the only difference is that here you sum up to infinity, but you don't divide by the eigenvalues. But then you can divide this. Well, this is just the Hilbert space norm. It's like the Euclidean norm in R to the power d. The Hilbert space norm is then just the sum of projections squared and then take the square root. Okay, we have our test statistic. Now, next step is always to get a test. We don't only need the test statistic, we also need critical values. And for the critical values, we need the limit distribution. So, for this, we write our test statistic as a function of a partial sum process. So this is a partial sum process SMT. That's 1 over square root n, sum I from 1 up to integer part of nt xi minus expectation of xi. So, yes?
It's probably remind me how the axis will rise.
Yeah, it's the projection on the eigenspace belonging to lambda head. So they will have different variances because, well, in some directions you have more variance than in others. Okay, it's partial sum process. The formula looks exactly like in the real valued partial sum process, but it takes now values in our Hilbert space. So now that's the first aims. We will find the limit distribution for our partial sum process. Then typically we have to deal with time series. We need observations over time to talk about the change point problem anyway. Right? So if we don't have a time order of our observations, then it doesn't make sense to say before we change you have this distribution, after we change you have that distribution. And if you have time order data, data sets typically they can also with dependence. Okay. And then if we have this, we can use continuous mapping theorem because our fully functional test statistic is a function of our partial sum process. And yes, so this was done in papers like dating over 10 years ago now. So, okay, so I will not talk too much about this in detail. So we need some dependence conditions. Yeah. Then we shortly have to discuss what's in the limit. So what's a Gaussian random variable in a Hilbert space? Well, it's a random variable where every projection has a normal distribution. Then we have to talk about an object called the covariance operator. So the covariance operator of X is a mapping from H to H. If you're not familiar with it, think of a finite dimensional case where you have a variance covariance matrix, which is D times D matrix. You can identify every D times D matrix with a mapping from R to D to R to power D. Now you just discuss this. I have the same with the Hilbert space. It's a mapping from H to H. And it's defined by the inner product of V of A and B is the covariance of the projection inner product of AX and inner product of BX. And what's now a Brownian motion? We need a Brownian motion because the limit in the one-dimensional case of a partial sum process is one-dimensional Brownian motion. Not so now we need a Hilbert space valued Brownian motion. So Brownian motion as a process with continuous sample paths and independent Gaussian increments, and just to say in the Hilbert space. And the covariance operator of an increment is given by time difference times this covariance operator. Okay. So now, under some moment and some dependence conditions, we have the Wick convergence in the square space of Hilbert space valued functions of our partial sum process to this Brownian motion W, where the covariance operator is given by this infinite sums of covariances. Now that's the same as if you work with time series, one-dimensional time series data. You could also vary something like called the long-run covariance, which is also the sum of all outer covariances. And then apply continuous mapping theory. We know the Wick convergence of this thing. This is a continuous mapping from square space to the real numbers. So this will then converge to the functional of the limit process. So it's the supremum of the norm of WT minus TW1. So if we had dimension 1, this would be just the supremum of a Brownian bridge, which is Kolmogorov-Smirnov distribution. You could look it up in tables. Now the problem is this is a multidimensional, no, infinite dimensional Brownian motion, so we cannot look up the critical values because they depend on the covariance structure. So we have this problem. We have a covariance operator which is hard to estimate, and the distribution is hard to evaluate. There are different proposals. You can use functional principal components, not for the test statistic, but for evaluating the limit distribution. Or you can use various types of bootstrap. So we have tried the block bootstrap, the dependent by2 bootstrap, functional autoaggressive sieve bootstrap. And because this is the newest thing, I want to talk a little bit about this. So what's the idea? Well, if you do time series analysis, often when you fit some simple R1, R2, R3 model, it captures the covariance structure quite well. Let's just many times used. Might not be exactly an R3 model, but the covariance structure is close enough to an R3 model where you don't really see the difference if you have some short sequence of observations. So, my idea is just to say, well, let's assume there's an autoregressive model behind, and we can estimate the parameters of this model. And then we can use this to generate pseudo observations and calculate our test statistics using this pseudo observation. So that's an autoregressive sieve bootstrap. And you can do this also for functional data. But then you have to estimate again, like now autocovariance operators. That's hard. So you use dimension reduction, again, not to calculate the test statistic, but to be able to fit this autoregressive model. And when you fit this on a finite dimensional space, then your residuals of this model will be infinite dimensional. Right? So you approximate something infinite dimensional by something finite dimensional. So you get infinite dimensional residuals automatically. And then if you like generate pseudo observations, you put the infinite dimensional residuals back, so you get infinite dimensional pseudo observations. Okay. And I should talk only 1 hour, I think, or less than 1 hour, so I skip you the details. Okay, so there are various bootstrap methods. Okay, so now what's about this weighted functional statistic, which I promise you? So for this, I remind you of our two test statistics, the dimension reduced and the fully functional, which are based on this QSUM statistics based on the projections. In one case, you sum them up to infinity. And in the second case, you sum only finitely many up, but you divide by these eigenvalues. Okay. So what can we do? We cannot put 1 divided by lambda hat p here. But what we can do is having 1 divided by lambda hat p plus lambda hat 1. Because this is always smaller than 1 divided by lambda 1. Lambda hat 1. So you're always smaller than the constant times this. So if this is summable, then this is also summable. On the same way, same time, now this gets, if lambda hat p gets smaller, this ratio becomes larger. So we have something little close to this where we give extra weight to higher eigenvalues to compensate that the variance is smaller in this direction. Okay, if you look at this statistic, when you see it's a compromise between the two, it's called the weighted functional statistic. But you could first think that this is not easy to calculate, right? So if you look at this formula, you might think, well, I have to estimate all these eigenvalues. And especially, well, at some point they are just zero. So estimating them is not a problem. But shortly before they are zero, they are very close to zero. So they are not so easy to estimate, maybe. Maybe you don't want to do it. But this is not a problem because you don't really have to estimate eigenvalues. You have to estimate the sums, which are much nicer to estimate. And then we also have this more elegant representation. So now we have our covariance operator plus lambda 1 hat plus, times the identity, and then we have to take the square root of this covariance operator and then the inverse, or the inverse when the square root is the same. Yes?
I have two questions. The first question is it not common to use a tuning parameter sequence like we do in Tikhonov in general instead of lambda at 1, theta n? I could
So-
imagine that you thought about that because that's
Yes, so we discussed it. So we really have to see, our aim is really like a compromise between the two. We have to think of something which is really in the middle and which is like for practitioners easy to use. So then this is easy to use because you don't have to think about tuning. And when really we see in the simulation, it offers a compromise. Okay, and the second question?
was the eigenvalues, are they not easy to estimate usually in that context? I mean,
Well,
at least rates are easy to divide, but
yes, when you look at these rates, so for example, they depend when on something like the difference between the eigenvalues and such things you get. So like,
the eigenvalues actually not, but the eigenfunctions.
true. Okay, yes, you have to also do the project, right?
Yeah.
Right, but here you don't have to project. Here in this representation, you don't have all of these programs. Okay. So if you don't know what the negative square root of an operator is, don't worry, it's the same as basically as a negative square root of a matrix. You replace you diagonalize it and you place the diagonal with the eigenvalues to the power minus 1/2. You can think of it like this. Okay. When something you shouldn't really use the estimated covariance operator of your observations if you have a time series data, if you have dependence in your data. Because, well, if you then project on your eigenfunctions, with projections are uncorrelated for the same time, but might be correlated for different time points. So this principal component analysis really works well for independent data, but if it is the right thing or not, for dependent data, you can debate, say, and many people think it's not the right thing. What you should do instead, you look at this long-run covariance operator and use the eigenvalues and eigenfunctions of this. This way, there might still be correlation, but over the long run, the correlation cancels out. And we want to do this partial sums, so we get this sum of autocovariance operators, so we are executing these situations. So now, these mu heads are just the eigenvalues as before, but not of a covariance operator of a single observations, but this long-run covariance operator. And now we get improved test statistic, which works like this, exactly as before, only with covariance operator replaced by a long-run covariance operator and the eigenvalue replaced with a respective eigenvalue. Okay, so this is our test statistic. So we have to do some assumptions. Some moments assumptions. Then some convergence assumptions on this autocovariance operators. So this is like convergence not in operator norm, but in trace norm if you're in functional analysis, but if you're not in functional analysis, don't worry, it's some stronger form of convergence. We have to be able to consistently estimate the covariance operator consistent in operator norm. We don't have to estimate all eigenvalues and eigenfunctions consistently. And when we have to, we just didn't want to deal with details of dependence conditions, so we just assumed that we have convergence of our partial subgroups. Okay. So when we get convergence of our weighted functional test statistic to this supremum of this infinite sum of squared Brownian bridges, so real valued squared Brownian bridges, well, this sum wouldn't converge if we wouldn't have these weights, and these weights come from this eigenvalues. Okay, now we have again a complicated limit. You might ask yourself the question if you can evaluate it. Yes, you can. You can do it either with bootstrap or you can estimate these ratios and then do some Monte Carlo simulations. Okay, so let me show you some simulation results. So we used n equals 50 observations, and we just use 21 Fourier bases. So in some sense, you could say it's multivariate data. It's really 21-dimensional. And sample size is 50. But well, if you would use multivariate methods in this situation, would be difficult. Okay, we have a change after 50% of the data. If we are under alternative for the null position, we have no change. When we have a functional autoregressive model, where we picked, and we have eta E, our say noise process in this functional autoregressive model, has a covariance structure with independent normals, but the variance of this is not the same. So either it might decrease fast, that means you're concentrated in few of the dimensions, or it might decrease slow, that means that your information is spread out over all the dimensions. So then you can use either the limit distribution, estimate our eigenvalues, and then Monte Carlo or bootstrap. And it turns out that it's the same for all test statistics, that the Monte Carlo tends to be conservative, the block bootstrap tends to be too liberal. And then in the later simulations, I only will show you the Monte Carlo results. But well, it's not totally unreasonable with percentages. Oh. Okay. So now we have the black curve is the weighted function statistic, the red one is dimension reduced, and the green one is fully functional. So you see here is the setup. Here you have a change in only few dimensions. Here you have in many dimensions. And we have a fast decay of eigenvalues here. If you have a fast decay of eigenvalues, then the dimension reduced statistic is the better one. The fully statistic is not so good, and the weighted function of the black curve is in the middle. Okay. Now we have a slow decay of eigenvalues. So the information is spread out about many dimensions. Then you have the dimension reduced, which was on top before, now performs rather poorly. And the weighted functional, the fully functional statistic, they perform quite similar. Even here, the weighted function will perform better. So we tried more scenarios. You will never find that we've never found that the weighted function statistic is the worst performing statistic. So somehow it's compromised. Sometimes it's in the middle, sometimes it's a bit closer to the better or the worse one. So in this sense, this is a compromise. Okay, so then I have 2 minutes to talk about gradual changes. So some data set. These are temperatures from the Mount Brocken, the highest mountain of the state where Magdeburg is in. And this is a long data set. Like 40 years of daily average temperatures, so 40 times 365. So you would say, oh, it's wonderful, I have lots of data, what's the problem? Of course, the problem is that temperatures from day to day are like highly correlated and very seasonal, so it's hard to work with. So what you can do, you can say, I take 1 year as one observation. So one observation is then a 365-dimensional vector, or you think of curve, temperature curve over 1 year is one observation. So here you see daily average temperatures in 1994. This is when one data point. Okay. Then to get a rough picture of what is happening, we want to do fully functional statistics, of course. We get the yearly averages, and you see an increase, not so surprising. You might say this is not really a change point because we don't have one point in time where it jumps up. Maybe you think something like this, oh, it looks rather stable and then starts to go upwards. So we don't want this model where the mean changes, but we have a gradual change. So we have, say, starting mean at some point on time, it starts by changes of the function g, which might then be a smooth function. So yes, there has been quite a lot of work already on this. So for a real valued case, it dates back to the 90s. But very recently, as I said, you can have different norms in function spaces. There was a paper by Dette and Bastian on this supremum norm and the space of continuous function. But I want to work in this L2 space and then also be able to apply this weighted functional approach. So let's look back at our test statistic. In the upper change case, we have this. We have as a mean the starting mean plus a change times the indicator that k is large. And then we can write our test statistic as the sum up to nt or the sum up to n. But if we take the sum up to n, we add the indicator that e is smaller than nt. So this is this function is basically the same, but 1 minus this function is this function. Okay. So now we have a different change g. If we would know the change, with the form of a change, we would just replace this indicator, which was the shape of a change before, by this g. We don't know g, so we just say we take a function h, which we think might be the type of change. So test statistic is the same before, only indicator replaced by an h. If h would be the indicator, we got our test statistic before. We could have a linear change, so we have constant periods when it goes up linearly, or it goes up like a square root, or it goes up like a square. What's important is you have always indicators, so you have a period where it's stable in the beginning. Okay. Now we can write down the limit. It looks similar as before, only here we don't have boundary bridges, we have some other covariance structures. Okay, well, we have to calculate it for every h. That's a complication, but of course, nowadays we have computers. Then we have a consistency result, so the test statistic goes to infinity under the alternative. Well, here we have to make some assumption, which basically is there is a little bit of correlation between the real j and the h. Doesn't have to be the correct function, but shouldn't be totally uncorrelated. Okay, now back to our data set. So we have the dimensional use test statistic with fully functional and the weighted function. And we have different types of function H we test. We don't know what's the function G, but well, we tested with 3. Here is the total variation explained. This is what I told you. So it shows the number of eigenvalues such that 80% of variation explained. And it means here we also already have to take 11 eigenvalues. We started with 21, so take half of them. So the dimension reduction is not really reducing the dimension a lot. But it's basically messing with the weights of the dimension. Okay. So let's see here. If you have an abrupt change and you have dimension reduction, then you get really high p-values. So you misspecified your type of change rather clearly. And then the information is spread out probably more than many directions, this doesn't work. So dimension reduced statistic gives you the highest p-values. Other p-values are closer to 5%. It's not a clear winner. So sometimes the fully functional statistic gives you low p-values, sometimes the weighted functional. And it's also not a clear winner of type of change. You can say, well, probably it's not abrupt. But if it's linear or it's like a square root, meaning it would be decelerating, or like a square, it would be accelerating. We cannot really tell from the statistic. Okay, so we have alternatives to dimension reduction. This is a fully statistic, which is there for like 12 years already. And now this new one, the weighted function statistic, you can get critical values with various bootstrap methods if you want to. And you can have now generalized our statistic also to be able to detect with gradual changes. So thank you very much for your attention.